The 10 stages of AI explained. Let's break them down. Stage 1. AI didn't appear overnight. It evolved step by step. Every revolution starts simple, and AI's first step was no exception. Stage 1 was rule-based systems, also called expert systems. These weren't learning machines. They followed strict if-then logic. If condition A, then do action B. Nothing more, nothing less. One famous example was MYCIN, a 1970s program that helped diagnose bacterial infections. Another was early chess software, which relied on pre-coded strategies rather than genuine adaptation. The strength of rule-based AI was consistency. It never forgot a rule. But the weakness was obvious. It couldn't learn. If the rules didn't cover a situation, the system failed. Rigid and narrow, this stage proved intelligence can't just be written in. It has to be learned. But rules alone weren't enough, and AI needed structure to reason more flexibly. Stage 2 was knowledge-based systems, built on symbolic reasoning and logic trees. Instead of just following instructions, these systems stored facts and relationships, then applied them to solve problems. Applications included early diagnostic tools in medicine and experimental legal advisory systems. They could mimic an expert's thought process, at least within narrow domains. The limitation? Scaling. Encoding human knowledge line by line was exhausting, and once complexity grew, the systems broke. They were brittle, collapsing under contradictions or missing data. This stage revealed quite an important truth. Real intelligence can't just be stored, it must adapt. The next leap came when AI stopped relying on humans to feed it rules. Stage 3 was machine learning. In simpler words, systems that learned directly from data. Instead of encoding every possibility, algorithms like linear regression and decision trees uncovered patterns themselves. This was a turning point. For the first time, AI could adapt. Given enough examples, it could predict housing prices, filter spam emails without anyone hand-coding every case, of course. The breakthrough wasn't perfect. Models needed large, labeled data sets, and poor data meant poor performance. But compared to brittle, rule-based systems, machine learning introduced adaptability. Here, AI began to shift from rigid programming toward genuine pattern recognition and dynamic problem-solving. But finding patterns in data wasn't the end. AI needed real perception. Stage 4 was deep learning, powered by neural networks with many layers. These architectures could automatically extract features from raw data instead of relying on humans to predefine them. Convolutional neural networks, CNNs, transformed image recognition, powering everything from medical imaging to facial recognition. Recurrent neural networks, RNNs, handled sequences like speech and text, laying the foundation for translation and voice assistance. The breakthrough was scale. With GPUs and vast data sets, deep learning crushed benchmarks in speech, vision, and translation. Its drawback? Data hunger and opacity. Models grew powerful but also black-boxed, raising new challenges in understanding and trust. But even now, intelligence stayed boxed into narrow boundaries. Talking about narrow, Stage 5 was narrow AI, or systems optimized for single tasks. Siri transcribes your voice. Google Translate converts one language to another. AlphaGo defeats the world champion in the ancient game of Go. Each example shows brilliance, but only in its own lane. I mean, Siri can't translate, and AlphaGo can't drive a car. Skills don't transfer, no matter how advanced the system is at one job. Narrow AI dominates today's landscape. It powers search engines, recommendation systems, and everyday apps. Yet it highlights the gap between specialized performance and true versatility. Here, AI proved powerful, but also limited by its singular focus. The real dream of AI has always been far bigger than this, though. Stage 6 is Artificial General Intelligence, or AGI. This is a system with human-level flexibility. Unlike narrow AI, AGI could reason across domains, learn any new task, and adapt on the fly. It wouldn't just follow data patterns, it would think. This stage is still theoretical. Some researchers predict AGI could emerge within decades, while others argue it may never be possible. The debate centers on feasibility, timelines, and whether current approaches like scaling deep learning can ever reach true general intelligence. For now, AGI remains an idea that defines both the ambition and uncertainty of AI's future. But if AGI ever arrives, the next stage could be even more unsettling. Stage 7 is superintelligent AI, also known as systems that surpass human capability entirely. Unlike us, they wouldn't just learn, they could improve themselves, creating loops of recursive self-enhancement. Each cycle could accelerate, leading to exponential intelligence far beyond human comprehension. This stage is speculative, but the implications dominate debates. How do you control something smarter than you? How do you align its goals with ours? Ethics, governance, and safety become urgent here, because while superintelligence remains theoretical, the risks it represents shapes how researchers, policymakers, and society think about AI today. Speculation aside, one stage of AI is already here in the real world. Stage 8 is autonomous AI systems, machines that can perceive, decide, and act in real time, too. Think self-driving cars navigating city streets, drones flying missions without constant human input, and robots handling logistics in warehouses. The defining trait is autonomy. These systems don't just process data, they respond directly to dynamic environments. They integrate sensors, decision-making models, and action systems in one loop. But limitations remain. Weather, unpredictability, and ethical dilemmas still challenge their safety. A car may master highways, yet fail at rare edge cases. Autonomous AI shows promise, but also exposes how difficult it is to trust machines with real-world consequences. But before machines outthink us, another stage is already reshaping daily work. At stage 9 comes collaborative AI, where systems act as co-pilots rather than replacements. This means that instead of competing with humans, they enhance us. Coding assistants suggest fixes. In medicine, for example, AI highlights anomalies in scans that doctors might miss. In design, generative tools brainstorm alongside creators. The value lies in augmentation. AI sharpens human decision-making, speeds up workflows, and expands creative possibilities. Yet it doesn't fully replace expertise. Remember, it just supports it. The caution is over-reliance. Humans must remain critical, questioning results rather than blindly trusting them. Collaborative AI works best when both sides, specifically humans first and then the machine, bring their strengths to the table. But power without direction risks chaos. And that brings us to stage 10, which is ethical and aligned AI. As models grow more capable, the focus shifts to governance, trust, and transparency. It's no longer about what AI can do, but whether it does it responsibly. Research centers on alignment, making sure AI goals match human values. Explainability tools aim to open the black box, helping us understand why systems make certain choices. Policymakers push frameworks like the EU AI Act, while labs explore technical safeguards. The future depends on this stage. True progress means coexistence, where human and AI goals align, making sure that intelligence serves rather than undermines society. But each stage may be even raising the same question. Is AI a tool we control, or a force that will define us?